So could something go wrong when you're trying to run an alter table command on a massive MySQL table? On November 27, 2021, GitHub had a major outage across their services like GitHub Actions, API request, code spaces, Git operations, pull request, and many more. And it all began with running a simple alter table command, but on a gigantic MySQL table. There is so much to learn from this outage. So in this video, let's dissect this outage and do an intense deep dive to extract 5 amazing insights about the database architecture, see their mitigation strategy, and a potential long-term fix. But before we move forward, I want to talk to you about a code-based course on system design that I have been running since March 2021. Right? If you are looking to learn system design from the first principles, this course is for you. Yeah. Because this is a cohort-based course, it will not just be me rambling a semi-optimized solution thinking it's the most amazing solution out there. Instead, it will be a collaborative environment where every single person who is part of the cohort can pitch in his or her ideas, and we will evolve our system around that. Right? Every single problem statement comes with a brainstorming session where we all together brainstorm and evolve our system. That's way everyone understands the kind of trade-offs we made while making that decision. Instead of just saying, hey, we'll use a particular queue, we'll have the justification why we use only that queue, why we use that particular database, why SQL, why not NoSQL, right? How are we leveraging throughput? How are we ensuring that our system scales? That's the highlight of this course. This course is taken by more than 500 engineers to date, spanning 9 countries and 7 cohorts, right? People from all top companies have taken this course, and the outline is very intriguing. It's very exciting. So we start with week 1 we start with the core foundation of the course where we design online offline indicator, then we try to design our own medium, then we go into database where we go in depth of database locking and see few very amazing examples of database locking in action, and how do we ensure that our system scales through that. Then the third week is all about going distributed where we design our load balancer. I'll walk you through the actual code of a toy load balancer and understand how TCP connections are managed and how simple it is to build load balancer. Then week 4 is all about social networks. Week 5 is all about building your own storage engines. Like we'll build that intuition on if you were to ever design your storage engine, how would you do that, right? Then week 6 is about building high throughput systems. 7 is about building IR systems, basically information retrieval systems and ad hoc designs, where we design our own message brokers like SQS, where we design distributed task scheduler. And we conclude the course with week 8, where we talk about the super clever algorithms that has powered or that has made those systems possible. Right? I have also attached a video verbatim as is from my first cohort where we designed and scaled Instagram notifications. I will highly encourage you to check this video out. Right? And now back to the video. So in order to dissect this outage, we will refer to the official blog post made by GitHub on this particular incident. I'll link this in the description down below. So what happened? In November, we experienced one incident resulting in significant impact and degraded state of availability for core GitHub services like GitHub Actions, API requests, code spaces, Git operations, issues, packages, pages, pull request. Almost every single thing that we use day in and day out was impacted by this. So what happened? We encountered a novel failure mode when processing a schema migration on a large MySQL table. Schema migrations are a common task at GitHub, often takes weeks to complete. What is schema migration? Schema migration is basically alter command that you fire in order to add a new column, delete a new column, update the data type of a particular column, create new indexes, all of that. This is typically what schema migration is all about. And it is so big that it often takes weeks to complete. Why? Let's dive into this first insight and understand why something as simple as an alter table command would take weeks to complete. Right? So alter table command is too slow for large tables. And why is it slow? Because with alter table, specifically when you are adding a new column, what would happen is if the entire row needs to be rewritten. Either you are using copy or you are using in place. So there are 2 ways to run alter command. You can either specify the algorithm, which basically MySQL calls it algorithm, as copy or in place. In either cases, the row needs to be rewritten. When the row needs to be rewritten, which means that a row is read, a new column is added, and that row is rewritten, and then the pointers are arranged in the B+3 node and all. Right? Because of which, if a table is large, it would have to go through all of those rows, add a new column, and then write it. I'm not sure what migrations GitHub did, but it could be something as big as this. So it could be as intense as adding a new column in most cases, because that's what takes the longest time. right? And be it copy, be it in place, the table is locked, or if you are doing an in place, the row is locked for some time and then it is rewritten with the new schema, right? So if your table is large, it will take larger time for you to run and complete the migration. And for those entire duration, the table or the rows, depending on what your database tuning is, they would be locked, right? So that impacts the performance, that impacts the overall throughput of your database. But most importantly, here, what it would definitely lead to is it would lead to a long time for your migration to complete, right? In most cases, you would see people preferring in place over copy, but even there is a third strategy to run that migration that we'll take a look at in some time. So then what happened? The final step in a migration is to perform a rename to move the updated table into the correct place. What are they talking about? Why migration rename? You just fired an alter query. Why would you have to rename something, right? So let's take a look on how big migrations are run. So although small migrations, you typically run alter table on that same table and you get those things done. But as I said, that whenever you are running alter table on gigantic or even a small table, it has to acquire locks on the rows, locks on the table in order to make those schema changes, right? If they are not acquiring locks, then it would result into some weirdish behavior for your end user. So that's where large migrations after a particular scale is something that your developer or your SRE team would do. And it's not like just simplifying alter table command. What people typically create is we create a new ghost table. Let's say you have a table called repositories, right? So in order to apply the changes onto this table, if I run alter table query on this table, it would acquire locks on rows, locks on tables, locks on DB pages and whatnot. So what SRE team or what database administrators do over here is whenever a gigantic migration is supposed to run or a migration is supposed to run on a huge table, we create a ghost table. For example, repositories, say we create repositories 1 table. This repositories 1 table may we copy everything from the repositories table to repositories 1 table. We first create a ghost repositories 1 table with no data, right? Then we alter the schema on this blank table. So it happens in a flash. Once the schema is changes, then we start copying the data from repositories table to repositories 1 table. And once the data copy is complete and both the tables are in sync, we rename the table. This is where basically this is exactly what the folks at GitHub are talking about. The final step of migration is renaming the table, so that now your repositories 1 would become repositories and you would be deleting your repositories table. So with this, without acquiring a lock on the rows or without or basically without affecting the throughput of your database, you were able to successfully apply a migration or a schema alteration onto your table, right? And this is exactly what MySQL does internally, but because it is doing it on the same table, it would have to acquire logs. But now when we do it explicitly, the steps that MySQL internally runs on alteration of a table, we do it explicitly so that we don't have to acquire locks on that particular table. And this does not degrade the performance of your database or acquire locks or affect throughput in any case, right? So because that is the final step, this particular step of renaming table repositories 1 to repositories is that step where the read replicas got stuck, right? Let's see what happened next. During the final step of migration, a significant portion, this is an interesting one, during the final step of migration, which means when they were trying to rename, during this final step of migration, a significant portion of our MySQL read replicas entered a semaphore deadlock. Read replicas entering a deadlock, pretty weird, right? Because deadlock happens when you acquire lock, like A waiting on B, B waiting on C, C waiting on D. But you would acquire locks when you are writing something. Isn't it strange to think that read replicas entering into a deadlock state, where like it's all read replicas, it's serving read requests, then where are these writes coming from? Who's writing to replica? The replication job, right? So while read replicas are serving read requests from the external users, there is this replication job that is continuously replicating data from the master onto the read replica. And when this replication is configured, what replication does? Replication reads the binlog file from the master, which means all the queries that were executed on the master, all the update queries that were executed on the master, they are sent to the read replica for them to execute it as part of the replication job. So that when a new row is inserted in the master, that row is replicated on the replica, right? And that is exactly how replication happens. So now writes are happening through the replication job. And if a write required to take a lock over here, that same lock will be taken on replica as well when the replication is being done. So when this happens, your replica can go in a deadlock state where your write acquired some locks, or sorry, when a replication job that you have written, when it is firing that update query, it might take lock, exclusive lock, shared lock, most probably exclusive lock. That's where the chances of deadlock comes in. Exclusive lock, it would take on rows, which is read by someone else, which is then read by someone else. So then the deadlock would happen. So writes, although they are not user-facing writes, or your main production traffic is not write on replica, but the replication job is the one who is writing to the replica, which is the one which is causing the deadlock onto replica. Right, and this typically happens when you have large amount of data that you would need to handle and migrate and whatnot. Right. Okay. So on MySQL, on MySQL cluster, our MySQL clusters consist of a primary node for write traffic, multiple read replicas for production traffic. Oh, this is an interesting one. Our MySQL clusters consist of a primary node for write traffic. This is typically your master node. Multiple read replicas for production traffic. Interesting. Everyone has that. And several replicas that serve internal read traffic for backup and analytics purpose. They are having two fleets of read replica. What is this architecture all about? Like, one few read replicas are okay, but why so many? Why multiple fleets of read replica? So here, what we learn from this is that, let's say this master has 6 replicas. Replica 1, 2, 3, 4, 5, 6. What you would typically want to do is you would want to typically have read replicas that are dedicated to serve production traffic. For example, like when we create an issue on GitHub, or when we create a PR on GitHub, and when we try to read them, that read goes to read replica, right? So you would not want to impact the user performance or the user experience. So that's why you would have a dedicated set of read replicas on which the production traffic comes in, the production read traffic comes in, right? And then obviously your main database that you have, you also want to run some analytics or backup or any internal systems, any internal services that requires that same database. Would you want to share the same read replicas that you did for production? No. You will create a different set of replicas, and these replicas are the one to which internal services use, like analytics, backup, and any other internal service. This way, the load on these 3 replicas, the top 3 replicas, are the one that is only handling the production grade traffic, while the bottom 3 replicas, they handle the internal traffic. So internal services, backup, restore, whatever they want to do. So this way there is this total segregation of responsibilities, and high production usage will not impact the other database. Internal database will not affect the main production read replica. This way, your analytics team can fire very gigantic queries onto this replica, and your production performance will not be impacted, right? So in most companies, you'll find this sort of similar, like this sort of architecture, where you would always have a few set of replicas dedicated for your internal teams, while the remaining set of read replicas for your actual production traffic that comes in, right? Okay, what next? What does this say next? The read replicas that hit the deadlock. Acha, remember the read replicas hit the deadlock, right? And then it entered a crash recovery state, causing an increased load on healthy read replicas. Due to cascading nature of this scenario, there were not enough active read replicas to handle production requests. So again, there are a lot of heavy words here. Read replicas that hit the deadlock entered a crash recovery state. What is a crash recovery state? Whenever your database crashes, the process would reboot. It would try to recover itself, right? And then because of heavy load, it would again crash. It would again recover, then again crash. So that is a crash recovery state where you are crashing and then recovering. But due to again load, you are again crashing and then again recovering. So that is because the load is not decreasing. The requests are continuously coming onto your infrastructure. There is no way for you to stop them. So that's why your read replicas are constantly going into this crash recovery state. And because of this, And one very important line that is written over here is that due to the cascading nature of this scenario, there were not enough active read replicas to handle production request. What happens over here? What is the cascading failure that they are talking about? So cascading failure mein what happens is, let's say you have 3 read replicas that were handling production traffic. One of the read replica went down, right? So let's say you had 100% of read traffic, the 3 read replicas shared them equally. So 33%, 33%, 33%, right? So each read replica was supposed to handle only 33% of the traffic, and it was provisioned to handle 33% of load. So if it required, let's say 32 GB RAM, it was given 32 GB RAM to execute, right? There was no over provisioning done. Now what happens is, let's say one of the read replicas go down. The load of this replica that went down is shared across the other 2 read replicas. So the read replica who had 32 GB RAM was supposed to handle, let's say 1000 requests per second, is now suddenly getting 1500 requests per second. So let's say the total number of requests that we were handling were 3000 requests per second on 3 read replicas, right? So each read replica handles 1000 requests per second. The third read replica went down. So the 1000 requests per second that went to read the third read replica, it will now go to the first and the second, right? And when that happens, the read replica that was configured to handle only 1000 requests per second is now bearing 1500 requests per second, 1.5x of load. So what would happen is that node would crash because it's not meant to handle 1500 requests per second. It is there configured to handle 1000 requests per second. So that would go down, and then it would put all the load onto the first. So now the only read replica you have needs to handle 3000 requests per second. That's insanely high. So this is what the cascading nature of failure comes in. So typically in every database architecture that you see, all of your database, not really exaggerating, all of your databases are prone to cascading failures. Because if one of the replicas go down, it would immediately transfer all the load, or your other replicas would have to bear all the load that was going to that replica along with the load that they were already bearing. So this is what is about database failure cascading. Every database is prone to this, right? So then how can we fix that? What can we do next to fix that particular problem? So there were not enough active read replicas to handle production requests, which impacted the availability. Obviously, you saw the cascading nature of it. Let's say 2 or 3 replicas went down. How are you handling read requests? Not possible, right? So which is why the outage happened. There were not enough read replicas to serve the read request. Writes were all working fine. Master was not affected. We are only talking about read replicas over here. Read replicas were not there. Cascading failure happened. The active read replica also started crashing, and they all went into this crash recovery loop, right? So this was the outage. This was why it happened. Now what did they do to mitigate it? During the incident mitigation, in an effort to increase capacity, because now what you would think, now in order to mitigate this outage, the natural tendency would be add more read replicas. How hard it can be, right? So in order to put an effort to increase the capacity, we promoted all available internal replicas that were in healthy state into production path. Now this is a very smart move. So what happens? In order to mitigate, so when an outage happens, you as an engineer, you would always be on your toes ki, let me first quickly get my site up and running. You don't care about anything else at that time. So when that happens, we know that we had 2 fleets of read replica, one handling the production traffic, one handling the internal traffic. Creating a read replica takes a long time, right? If there are ways to basically speed up the entire process, but it would still take a long time. When the mitigation is happening, you don't have enough time to some of the engineers would have created or basically would have initiated the creation of read replicas, not denying that. But in order to mitigate, you would find the quickest hack to get your site up and running. So you wanted to increase the capacity on your production fleet, because on your production fleet, you had 3 read replicas, out of which 2 were down and only one was handling one was barely handling the request, right? So now what you wanted to increase the capacity, which means you wanted to add more read replicas. But creating new read replicas might take time. But you anyway initiated the creation of read replica, which let's say might take 10 minutes, 15 minutes for it to spin up. So what can you do to quickly mitigate this? what their engineers did is, because there were like other fleet of read replicas replicating from the same master node, but they were serving internal traffic, they literally promoted the node from their internal fleet into their production fleet. So now that read replica that was earlier serving internal traffic is now serving production traffic. So they very quickly moved all of their internal replicas, because let the internal team suffer, that is okay. External traffic should not, or the main github.com website should be up and running as soon as possible. So they basically promoted all of their internal read replicas into external read replicas. So basically just changed, now they basically added it to this fleet so that they can now serve the traffic, the production read traffic. And that's how they quickly increase their production read replica capacity. But it did not work. It did not work because of the heavy load. So now what happened? When they promoted this existing read replicas into the production fleet, what happened? Because of the heavy load, the new replicas also started crashing, because the external load is not stopping. Because the external load is not stopping, what's happening? Because the writes are being the writes are being served, right? You just like all of your read replicas are affected, but your writes are being served. So the read loads is still coming to your production read replica fleet. The newly added replicas which were promoted from the internal fleet to your external production facing fleet, they also started crashing because of heavy load. Because as soon as the load happened, your replica started crashing, right? The replicas that were crashed, they recovered, they again crashed. This was the crash recovery loop which all of the replicas they were stuck in, right? So the shift was not sufficient for the full recovery. We also observed that the read replicas serving production traffic would temporarily recover from the crash recovery state, only to crash again due to load. So the load was so high that even if they added the machines from your internal fleet to this and added more replica, it started crashing and crashing and crashing and crashing, right? So there was no way for this to be fixed. Like, it was getting affected so much because the load was so high that even this promotion, this quick hack was not working. So based on this crash recovery loop, we choose to prioritize. This is one of the most brilliant point I ever read. Do understand how organizations think, right? Like a great organization like GitHub, what they said, based on the crash recovery loop, because your replicas were crashed, they recovered and they crashed again. Because of this crash recovery loop, we chose to prioritize data integrity over site availability by proactively removing production traffic from broken replicas until they were able to successfully process the table rename. This is one of the most beautiful thing that an organization can do. Like, this shows you how thoughtful they are when that outage happens, like how important is data for everyone. This shows you that. What they did is they prioritized data integrity over availability. So when your replicas are continuously recovering and crashing and recovering and crashing and recovering and crashing, it is anyway have affected your availability, right? So which means that you have accepted the fact that your website is down and your core services are down. But what you would want to prevent is you want to prevent data integrity, which means that no matter how many times the corruption happens, no matter how many times the crash happens, your data should not be corrupted, right? So you choose data integrity, because if your data becomes inconsistent or if your data is corrupted, it would take far longer of an effort to fix that as compared to anything else, because how do you even know what's the source and what's the truth and what's not, right? But if you notice, aren't these the read replicas that were going down? Why are they talking about data integrity? Well, because data integrity would be at loss when your data goes in an inconsistent state or while writing the data it is corrupt. But who is writing on read replica? Replication job, right? So when your read replicas were constantly recovering from the crash and again going down, what might have happened, because your read replica came up, it started replicating from the master, so it started pulling in latest changes from the master, and then it crashed. It recovered, it started pulling changes from the master, and then it crashed while handling all the load that is coming in. So what is happening is the write here is happening from the replication job. The reads, then you are getting constant read traffics happening on the replica. So the data on the replica could corrupt because during this replication job, let's say the replication job asked a replica to fire an update on a particular row, and while updating the database, while like let's say there was a bulk update on 100 rows, while just updating it for 50 rows, your database crashed, and due to any reason, any bug in the existing software, anything, your data could corrupt, right? So you do not want your replicas to corrupt because it would take far larger effort for you to solve for that versus just getting your site up and running. So in order to protect your replica from not going corrupt or from not getting corrupted, they chose to let it crash and they removed it out of their production fleet. Right? And now when they removed it out of their production fleet, what happened is that now they stopped getting read request on that read replica, and it had time to complete the schema migration that everything started with, right? Because why your replication started failing? Because there was a deadlock. Why there was a deadlock? Because there was a schema migration that was happening, right? So now what did they do is they let the replica crash. They let the crashed replica not handle any traffic, which means they removed the replica out of their production fleet. Then they gave replica the breathing space it needed for it to complete its schema migration. With ease, then the replica completed their schema migration. Once it knew that it's fully recovered, not corrupted, then it added back that replica into the production fleet. This way, the breathing space that the replica needed, which it was not getting because of high read load coming in from the production traffic, it got that space so it can complete the migration with ease. And once that is done, they added the read replica onto the production fleet. I'll say, but the load is there, it would still fail. But think about it. The failure happened because of deadlocks. If deadlocks would not be there, your read replicas would very easily handle the load. Right? Because of the logs that were taken, because of the deadlocks that were taken, the load or the CPU load or the processing load was increased onto a system because it was all waiting. Your IO wait time increased by a massive margin there. So once that all was done, then you slowly started adding replicas, and then slowly the entire capacity was restored. The entire outage happened for 2 hours and 15 minutes. And to be really honest, whenever there is an outage like this, in most cases, a circuit breaker would have really helped. You typically see that a lot of, with help of circuit breaker, you would have stopped the traffic coming in onto a read replica, let the read suffer, let your replica get time for it to apply the migration, and then basically be healthy and start serving the production request. Okay, just on the conclusion part, once the replicas recovered, we were able to move them back into production and restore enough capacity to return to normal operations. And it all took 2 hours and 50 minutes to do it. Throughout the incident, write operations remained healthy. Master had no idea. Master literally had no idea what was happening, what kind of chaos that happened behind the scene. It was all happy and handling all the write requests coming in. But reads were the one that were affected by a huge margin. So when the writes operation remained healthy, and when an outage like this happens, when there is a lot of crashes and recoveries happening, you always have to check for data corruption. That is your MySQL table corrupted. So there are commands to check if your table is corrupted or not. It typically depends on the database. These folks use MySQL. So basically folks at GitHub use MySQL. So MySQL, they ran that corresponding command to check for the corruption of the table. If it is corrupted, then there are ways to recover it. That's a little bit of MySQL in terms. You can Google about it. You'll learn a lot about, you can learn a few details about table corruption and recovery from that. Right. Now, what did these folks do in order to do that long-term fix? Now, because obviously whenever there is an outage, you have to do that long-term fix, right? So what's the long-term fix over here? So the long-term fix that they're talking about is they're talking about something that to address this class of failures and reduce time to recover. See, they are not only focused on eliminating the error, because you have to be wary of the fact that failures will happen, outages will happen. So to address this class of failures and reduce the time to recover, The main problem of this outage was not that it failed. Schema migrations, things would go wrong. You cannot predict the production traffic or the production load that is coming onto your replica. But you should not be taking 2 hours and 50 minutes to recover from that. So then what do we do to solve it? They said that they would continue to prioritize their efforts in functional partitioning efforts. They would prioritize their thing about functional partitioning. We'll talk about functional partitioning. What exactly is that? So what is functional partitioning? So what GitHub is doing there? So this is that one place where you see vertical partitioning in action. So what happened is they have this one gigantic database in which they have multiple tables, like let's say repositories table, pull request table, and issues table, and actions and webhooks. Everyone has their own, like there are tables for every use case that you could think of, right? But because of this database become huge because everything is stored in this one database, right? So now what would happen is when you are running a migration, then all of the services, because they all rely on the same database, they all get affected. So what they are doing is they are doing functional partition. So which means that a pull request function needs its own database, an issues function needs its own database, let's say a comments function needs its own database and all, right? So this is what functional partitioning is all about. So you typically create smaller databases with the exact same table. So this is not data sharding, this is not data partitioning, this is not horizontal partitioning, this is vertical partitioning. We are literally taking all the data of a table and putting it into a separate database. So basically creating multiple databases out of, kind of like microservices. Not exactly, but kind of like microservices, right? So they are just vertically partitioning their database so that this big gigantic database gets split into smaller databases, each having a few set of tables, which are very high cohesive, which means that all the tables required for you to function or pull request will go to this one database. All the tables required for you to power issues on GitHub will go to this database, right? So functional partitioning is what they are talking about over here. This is this one place where you'll do, this is basically the idea of vertical partitioning as well, right? What advantages would we get by this? With this, because you don't have one gigantic table, you have smaller tables, your migrations can run on a small database server before on production. Right now, when they applied the migration, they applied it on the main production DB, right? But was there a way for it to test it before? Like they would have tested on a smaller set of data, but not the complete data, right? So that would have been extremely difficult given the size of the database. So that's why by doing this vertical partitioning or this functional partitioning, they can run a canary. What is a canary? Canary is a small database server or small API server, depending on what you're doing. In this case, it's a small database server in which you are running your migration just to test if everything is working fine. Because this database would be much smaller as compared to this one gigantic database, what you'll get is you can actually test your migration on an actual data before hitting the actual production. Big advantage, right? And second, if your database goes down due to any reason, because of unforeseen circumstances, it will not affect others, which means that if you wanted to run a schema migration for your pull request table, it would not affect other databases or other tables which are present in other databases, right? So you are reducing your blast radius. So your mean time to recover drops down drastically. So you'll have, like, even if some outage happens, your other services are working fine. You don't have to think, because here the migration, let's say the migration happened on pull request table, but because in the current architecture, the pull request table, issues, webhooks, everything lied in that one database. The entire database got affected, which affected all the services. But if it would have been functionally partitioned, then the migration that you have applied on the pull request table would have only affected the database holding the pull request table. Like you are not even firing other databases, right? So that is a big advantage that you will get out of doing this functional partitioning, which is what the team at GitHub is also prioritizing their efforts on. Partitioning the cluster adds resiliency given migrations can then be run in a canary mode on a single shard, reducing the potential impact of this failure. Additionally, we are actively updating our internal procedures to increase the amount of each cluster is over provisioned. This is an important one. The second biggest reason why this outage happened was that when one replica went down, the load came onto the other two. That other two were not provisioned enough to handle 1.5x load. So that's what these folks are talking about, where they would need to update the internal procedures to increase the amount of each cluster is over provisioned. Which means that if it required them 32 GB of RAM to process 1000 requests per second, instead of giving 32 GB, let's give it 64 GB. So that even if one of the replica goes down and the load moves to other read replica, they are provisioned to handle that much of load. Right? This is an excellent thing where you will find most of the organizations are typically over provisioning their databases just to handle scenarios like this. If you are if you are a senior engineer, go audit your infrastructure for this particular use case. Have your database a little bit over provisioned just to handle loads due to failures of other load because of failures of other peripheral components. Right. So as the next steps, we are continuing to investigate the specific failure scenarios, and we have paused schema migrations until we know that no more we have safeguarded against this issue. So they've stopped database schema migrations until they're pretty sure that if they run a migration again, they would not see this error again, right? So they have safeguarded against this particular issue, then only they'll start applying the schema migrations again. As we continue to test our migration tooling, we classify opportunities to improve it during such scenarios. That's an interesting one. You get to learn so much from these outages. And this is exactly how real life firefighting during production outage is all about. You have to be very quick, very witty in order to mitigate this issue. So nice. I hope basically that's it for this video. I hope you guys liked this one. If you guys liked it, give this video a massive thumbs up. If you guys like this channel, give this channel a sub. I post 3 in-depth engineering videos every week, and I'll see you in the next one. Thanks, Ata.